real-time application use cases. Then I will pass on to Sharon, our technical expert, to give you a hands-on demo and training on how to use Vissim for the highway simulations. Okay, so yeah, here is an overview of the integrated end-to-end transport modeling and simulation solution from PTV to support you with the transportation planning, traffic engineering, and also master planning, as well as policy research and analysis. So we have a macroscopic citywide and regional-wide simulation, and this is also multi-modal traffic planning and modeling with Visum, as well as Model2Go, which is the technology which we can generate a base transportation model of the both supply and demand in less than 1 week for any city. We also offer currently PTV Lines, which is a SaaS products and helps the public transport operators and the authorities for the service planning, network design, and also accessibility studies. And for the microscopic simulation aspects, which I think most of you are very familiar with Vissim and Viswalk for the multimodal traffic simulation and the microscopic simulation for the pedestrian, and Vistro as well for the TIA and also signal optimization. For real-time products, we also have Optima and Flows, which helps for the traffic prediction for the next 1 hour and also real-time decision support for both highways and also urban roads. It also supports real-time data integration, and also currently we have PTV Flows, which is completely based on cloud and also based on the TomTom speed data. And lastly, we also have a hardware like Evo Radar, which can help to detect vehicles and also pedestrians, motorcycles, and also it can help basically to monitor and collect the traffic data. And before we jump into the detail for today's session for the highway simulation, we would like to first give a quick introduction on PTV Hub, which is our newly released cloud-based platform integrating the online tools with the desktop licenses for Visum, Vissim, Viswalk, and Vistro. So basically, PTV Hub works only with the subscription licenses, and then with the Hub subscription licenses, and you can easily access and share content, and also sharing models and results across the different organizations. And there's also very rich like dashboard functionalities. So besides the calculation part, we can also enable you to upload the Visum model and Vissim model to the cloud, and then you can run different type of analysis and visualization on the PTV Hub. And after the calculation and the result visualization, you can also share this kind of a dashboard with either your colleagues, the management, and also with the general public or your customer as well, so that they can be aligned on the same page with the model results. And besides Vissim Visum, we also enable export the Vistro data into the Hub as well. And here there's an example for exporting the Vissim data. You can select how many simulation run, what is the time interval, and also you can customize what kind of result you want to visualize on the Hub dashboard. And this is also very helpful for the communication with the end customer as well on the different design and the scenario comparison. And it's very easy also to create the visualization as 3D animations with PTV Hub based on the vehicle trajectories. Okay, so we will be having another separate session on PTV Hub. Yeah, so the challenges for currently the modern highway and also the traffic management is that mainly currently the highway are facing a lot of pressures from the land use and also population growth, urban expansions, increased logistic traffic, and also expectation from the authorities and from the general public on the more efficient road and greener and safer travels. And expanding the highway isn't just about adding more lanes, it's also about optimizing the existing traffic flow and also maximizing the use of the capacity and also making the informed decision based on the real-time data. That's why we can make use of the vehicle simulation and the modeling tools to achieve such goals. So we have 3 different products for highway management and planning. So the first one is PTV Visum, which is a highway planning tool. It can help to optimize your long-term investment and also can help to predict the long-term network performance, demand, and also you can manage the short-term network performances as well. And it's an industry standard for macroscopic modeling and multi-modal transport planning and can help you to answer a lot of what-if questions for the highway. The key functionalities for the highway, including the demand modeling for the prediction of the future demand and road choices on the corridor, comparison of the different scenarios for the capacity expansion, tolling, or policy changes. And also you can conduct intermodal integration to analyze the mode shift between highways, public transport, and freight. You can also conduct cost-benefit analysis. And with the use of the SVA, which is Visum simulation-based assignment, you can also use Visum to analyze temporary traffic management strategies. And also, if you block certain lanes or if you have bus-only lanes, so this kind of lane level analysis can be also done in Visum right now, besides the long-term planning and also planning for the new infrastructure. For Vissim, we can use Vissim to run the detailed operational analysis for the highways, and it can replicate the real-world driving behavior for the highway design and control. Later, we can also show you some examples in other cities for simulating the complex highway and interchanges. And the key capabilities also include the lane level analysis for the merging, weaving, and ramp behavior, signal and ramp metering control, CAV testing, and also driver behavior calibration. And you can also use it for testing different ITS strategies. For example, the VMS signs and also speed control, dynamic lane management, as well as the shoulder lane opening and closure. In terms of the real time, so we also have customers who are interested to incorporate the real time data on the highways for the traffic management and prediction, especially considering the real time event and also real time incidents. So in this case, we can use PTV optimal flows for this type of real time management and decision support. And the typical use cases including the managing the daily traffic for peak hour, incident response, and also construction event management, as well as other type of scenario comparison and the data integration. Okay, so let's start with the PTV Visum use cases, our macroscopic modeling tool. So one of the projects that has been using Visum and Vissim for highway is the Sofia Ring Road. So Sofia is the capital city of Bulgaria, and there's increase in population and vehicle use. And also there's a need for the road infrastructure upgrade, especially for the highway. This is marked in the dark blue areas. So this 8-kilometer road currently are being used for the feasibility studies and also analyzing the key issues like lane capacity, interchange design, traffic distribution. So the obstacles faced by the project team is the lack of a traffic model because there's limited data, insufficient camera data, not enough for the OD matrix, and also some budget constraints. And by overcoming the data limitation, the project team has used Visum to create a transportation model. So they have used traffic count data from 10 key junctions, as you can see near the project areas, and also they have set up videos for recording the footages and using deep learning algorithms to derive the traffic count for different vehicle classes. And in total, about 50 zone OD matrix was created. And also the Visum's T-flow fuzzy OD estimation methods has been used to ensure that the matrix is closely mirrored with the real-world traffic pattern. And then the second step is mainly assigning the traffic volume to the network and the validation and to ensure that there's a high accuracy achieved and that the model reflected the real-world conditions. And finally, they have used Visum to forecast the demand for 2030, considering the population growth, infrastructure plans, and also making use of the model to show the traffic shift to local roads after the completion of the construction of this new section. Different design alternatives are also compared, including one-way roads, links, and also different traffic volumes. After that, this PTV Vissim has been also used, and the demand data and the traffic data network from Visum can be exported to Vissim for a more detailed analysis, especially on one of the key roundabout interchange where this ring road meet the highway. So using Vissim, in total, about 4 different design scenarios are tested. And then the weaving section especially are analyzed. And also comparing different entry and exit design to recommend the solution to enhance the traffic flow and reduce the congestion at these key points. So the second use case is using Visum is the modernization of the Berlin's motorway network, which is integrated traffic and construction concept. This study is studying the A111 motorway, which is a very crucial corridors connecting Berlin to the city center. There is a very high traffic volume on the daily basis. And this model is used to support this comprehensive transport master plan to address the current challenges and also to understand the future demand. So the Vissim model has been used to assess the current traffic as well as prediction what the traffic condition will be like in 2030. And in this case, also developing different strategies to manage the traffic congestion and also enhance the traffic flow. The model also integrates the multimodal transportation, including public transport, cycling infrastructure, and also ensure environmental sustainabilities. And in this case, there's a few strategy recommendation has been made based on the Vissim model to the government and authority. So the first one is the infrastructure enhancement. So certain segment can be widening of the certain segment to accommodate the increased traffic volume in 2030. And also upgrading of a few interchanges to improve the traffic flow. And also multimodal integration of the park and ride facilities and the expansion of some of the cycling infrastructure parallel to the motorway, as well as the ITS strategies, which can be used to better manage the real-time traffic, and also dynamic speed limitation, and also lane management as well. Yeah, so this has been used to address the key mobility challenges and help to make informed decisions. And then comes PTV Vissim, our microscopic simulation tool. The use cases in China, Shenzhen, one of the highway expansion project, and also has been used in Japan for highway vehicle to infrastructure communication project. So if Vissim tells you what might happen, so Vissim can tell you how it will happen in detail on the land level. So we use it in Shenzhen. So this is a Jihe Expressway dual level upgrade. So also it's the first project where there is a ground and elevated highway that they stack together. And you can see it's a very long highway, and there are about more than 20 interchanges along the way, and a lot of these sections are very congested. And also the daily very severe congestion at certain locations, over 150,000 PCU per day, and projected to exceed 200,000 PCU per day. And in this case, we have used Vissim mainly to handle this project. So this integrated Vissim not only with historic data, but also with collected big data, and also traffic models, 8 degree of freedom driving simulator are also applied to this project. And the result of the model is about over 90% accuracy of the model, and also realistic replication of the traffic condition along this Jihe corridor. And as you can see that while during the process of building the model, so a lot of data are being collected in the field and also with the driving simulator. And so this diagram also shows for the HGV vehicles driving on the slope and then the speed distribution and also the speed changes at the different location of this particular slope. And also other data are collected like vehicle speed. So it shows the speed distribution for different road types. So the blue one shows the basic road section, and the others are showing like the merging areas and also the curve areas for the main roads, and also the ramps for the interchanges. So there's different vehicle speed distribution. And also for the night times, so there are also different speed distributions, and also comparing this with the default speed distribution in Vissim. For the car following distances, so quite extensive data also collected and calibrated. So there are different vehicle composition at the overtaking lane and the through lane, so leading to a smaller headways between the vehicles than the through lane. On the overtaking lane has a smaller headways actually. So all these parameters are put into the model, and then also the model is integrated with the BEAM software to provide a better visualization of the simulation result. Okay, the next example is the Car2X example. So this is example case study with Toyota, and also study the possibility of improving traffic congestion on expressway by using the connected systems. And this is mainly focusing on the connected highway merging areas, aiming to maintain the speed after the merging. This is considered building a system architecture on the cloud server as well as a future scenario that we don't need special infrastructure, but only the communication system. So the cloud systems will get the traffic information from the connected cars and then send the request to such as keeping lane or changing speed to optimize the traffic flow. And this virtual test environment is built together with MATLAB and Vissim. So for the MATLAB, both software are communicated together by the COM interface. So MATLAB will get the traffic information such as the position, speed, and lane from Vissim. And then it will also send the command such as the target length, target speed to the Vissim for this driving, for this testing of the traffic flow. And this gives the optimal system and estimation of the social impact as well. These systems can help to identify the optimal system parameter and identify the social impact before the installation to the real world. And the purpose of the control system is mainly to eliminate the factor that cause the speed reduction after the merging. For example, the analysis of the traffic condition can show that the speed reduction in the driving lane due to the merging and also the speed reduction in the overtaking lane due to the lane change were observed as well. And also can help to verify the three type of vehicle control system for the more smoother traffic flow. Like for example, the lane change guidance before merging areas, or you have the lane change prohibition after merging, or you have the improved response with ACC operation. So different type of this can be tested in Vissim to showcase the result. And this is basically showing the ACC operation was conformed from the simulation to be the most efficient of the three types. And then you can see the comparison of the simulation without control and with the ACC control. So the color of the vehicle is representing the speed. The blue one is representing the higher speed, and the brown one is closer to the lower speed. And although under the same condition at the same time of day, it can be clearly seen that the wave of the traffic congestion has been suppressed by the increased following response by the ACC here. And lastly, we would like to show some real-time operation. For the real-time products, PTV Optima and the flows can help with the highway management and the real-time control. So for Optima, it's possible to collect different type of detector data, sensor data, camera data, and also the speed data to fuse into one data source and provide the prediction for up to 1 hour. So the result for the monitored result on the key paths and the different alternative paths can be then communicated to the users through the VMS panels. And this is also done by integrating the data and also the ITS devices to Optima through the API interfaces. And then the second product for real time is PTV Flows, which is a SaaS product and is available in 84 countries. And mainly it helps to manage the traffic proactively, sending alerts where there's a congestion and also improving the safety and efficiency of the entire system. And we also offer the historical data analysis module right now that you can make use of the historical up to 1 month, 6 months, or 1 year data in your database, and you can retrieve the historical data and to understand the traffic pattern, travel times, and also the traffic status. So the application use cases including one of the project in Hungary, which is the implementation on the Hungary highways. And in this project, we use Optima and Visum to deliver to the Hungarian public road. And this model provides the traffic simulation for the control center and also make use of the INRIX data, count data, and also event data to calculate the traffic prediction every 6 minutes for the next 1 hour. And for PTV Flows, there are also some new use case applications. So for the highway authority in France, they have been using Flows to monitor the highway traffic in real time and communicate travel times through the VMS. And for the port as well, so for the port of Rotterdam, they also use it to predict the port arrival time of truck on the main path and to use trucks to extract the speed data and also analyze the data for improvements in the arrival and egress time. There are also some special use cases like Texas TV station, so it's customizable and easy to use GUI to display the traffic news during the TV broadcast. And also public authorities like in US Cranberry, So they are also using traffic response for the integrated corridor management and incident response on the highway. Okay, so this is an introduction and overview of the solutions for PTV modeling and simulation. Next, I will pass to Sharon for the detailed demo and also the modeling technique sharing for the PTV Vissim for highway simulation.
Thank you, yes. So I hope everyone can hear me. Let me share my screen first. Okay, so yeah, I hope everyone can see my screen. Thank you, for sharing the use cases and giving a, brief of our products. So what we will be learning today is mostly about how we do highway modeling in Vissim. So for highway modeling in Vissim, we have a few examples plus few features that we want to showcase with you. So the first thing will be the network geometry, and then second we'll be learning about the things that we need to do to the driving behavior and how we can calibrate them for highway modeling, and we'll be learning about vehicle actuated programming and how we use vehicle actuated programming in Vissim using VisWap, and we'll be learning an example about hard shoulders, and we'll be also learning about how ramp metering works in Vissim, and we'll also see an example on variable message signs. The model is created using attribute modification. And please keep your questions to the end. So we will have some time for Q&As, and we'll be sharing all the materials, that is the presentation used and the models that is showcased. Everything will be shared after the webinar is over. So I'll not be going full screen since I need to switch between Vissim and the presentation. So I'll just keep it in this mode. Okay, let's go. So the first thing that we'll be talking about is the network geometry. As you all know, that PTV from PTV 2025, we have made a huge change with regards to network geometry, which is when you're connecting two links of different number of lanes. Visim now will be automatically able to connect it without you creating like if there is a difference between, like if let's say like there is a four lane and you want to connect it to a two lane, previously what you'll do is you'll connect the two lanes to two lanes first, and then the rest of the two lanes will be connected with a separate connector again. So to reduce the work of a modeler, what we did was we brought in the new connector feature where Vissim will automatically be able to judge what type of connector is required, and then it will create the connector by itself. So this feature is very helpful when it comes to highway modeling, because when it comes to highways, you'll not have you'll not have continuous four lanes or continuous six lanes or continuous three lanes. You'll have like two different three lanes and two lane links merging together to a common six lane highway, and you'll have like merging diverging happening at various points of the highway. So for these kind of situations, this particular feature will be very helpful. So let's move on to the examples. So yeah, so when you receive your files, it will have like the presentation, plus it will have a folder called model files. This model file will have the models for each of the examples that we will be going through later. So let me open the geometry model first. So always remember to use 2025, because whatever we are learning today is based on the latest version of the software, based on the latest update that we provided for 2025. Okay. So I'm opening the model geometry, and I'm opening an example that I have for this session. Before we go into the example in detail, I'll show you how connector works in a small example first. Okay? So this is the example that we will be working on after we know how, after we learn how connectors works. So let's say we have a link here and we say it is a 4-lane link. And then we have another link close by, but this link is a 2-lane link. So previously, when you connect these two links, what happens is you'll be first connecting the 2-lane to 2-lane, and then you'll be connecting the next 2-lane to 2-lane, and then you'll be like adding in a intermediate points. So this is how it works when you are. This is how it works when you are using like versions below 2025, which is 2024 and below. But if you use 2025, what happens is it will just Vissim will just directly create the connector for you for all the 4-lane to 2-lane. So here you can see there is a smaller like merging lane on both the end, and then there is two main lane in the middle. So likewise, this particular feature will be useful for you when you are modeling highways with different number of lane compositions. Okay, so we learned how this particular connector feature works. So let's move to the example that we have. So before moving to the example, okay, yeah, we will do the example first. So if you see this example, we have 2 lanes and a separate 3-lane link merging together at this point to form a 5-lane, and later it becomes 4-lane. Okay. So now we have to model it one by one. So when you have scenarios like this, what you have to do is you need to have a smaller intermediate link so that it's easier for you when you connect from different links to different links. So this is the link that I have created with 5 different lanes, and then what I'm gonna do is Vissim, like the new connector feature that we have in Vissim is based on the destination link. So it always focuses on the destination link, and then it will create all the connector lanes. Okay. So when I create a connector all the way from here to here, what happens is based on the destination links configuration, it automatically creates the connector. So I'll just click OK. And if you see, based on whatever configuration that the destination link has, it will create something like this. But this particular configuration looks like it doesn't look right because we don't have like a no lane change regulation at this point. So what we need to do is here we are going to use the connector feature. So first, if you see here, always you will get these kind of rectangular boxes, which indicates you can adjust at these points. So what I'm gonna do first is let me reduce it, and then let me focus on first 2 lanes. So I'll just move this yellow dots to here. So let me finish the first 2 lanes, and then I'll move on to the other lanes. Okay. So because I want to do this 2 lanes first, so I'll just reduce this, and I'll also do reduce this. Now I have converted a 2-lane merging into a single lane at here. Now I'm gonna extend this. Like gradually you can use this point to extend this. If you want to extend only at the end and don't want to affect this one, you can use this particular rectangle box. But let's say you want to extend the whole connector, then you can use the middle one to extend all the way to the end. And if you see, there is a short lane at the end as well. So we are extending till the short lane. Now, if you see here, let me make this one bigger. Now, what I'm gonna do is, for this geometry, what is happening is we have these two lanes getting priority over these three lanes because this is the through movement. Like this is the most probably this will have the higher traffic. So because it's coming all the way from here, since there is like some curvature happening, the traffic will be slowed down. But this particular link has very high traffic, and if you see, this particular two lane needs to get priority. But in Vissim, you cannot give priority to two lanes at a time. So what I'm gonna do is I'm gonna give only priority to the rightmost lane. So to give priority to the rightmost lane, what I'm gonna do is I'm just gonna make sure none of the traffic from the next lane plus the additional three lanes on the next link to affect this. So I don't want any of the traffic to affect this particular one. So what I'm gonna do is I'm gonna close the lanes for this particular connector. So you can see here, there is no lane change for left for all vehicle, no lane change right for all vehicle. So I'm just gonna close it. So now if you see, no lane change will be happening at the rightmost lane. So it gets the whole, like it gets the complete priority and it will not be affected by the neighboring movements. Okay. So let me run the model. Let's see what is the error. So it says static vehicle route is not complete because we have created this connector just now. So to complete the static vehicle route, what I'm going to do is I'm just going to click on the destination of the static vehicle route and I'll just move it up and down. So it will auto calculate that particular static vehicle route. So if you see, it has broken static vehicle route. So I'm just going to move up and down. So it recalculates. So both my static vehicle routes are complete. So if I zoom in, both my static vehicle routes are complete. So let me run the model again. Now let's see how it looks like. Let me fasten the simulation. So if you see here, in this particular link, what is happening is we see very least amount of vehicles or even no vehicles are using this particular merging lane. Like this particular like smaller merging lane, which is the second lane of the link 10002, we can see none of the vehicle are using this particular link. The reason is we have lane changing distance. Like by default, the lane changing distance for any connector is 200 meters. So since the lane changing distance is 200 meters and the emergency stop position for any connector is 35 meters by default. So 35 meter or 30% of the whole connector link. So it should be changing lane, or if it is not able to change lane, it should stop here till there is no movement and then it will change lane and then it will start going. But since the lane change distance is very high, what happens is the vehicle will be able to take decision somewhere before even coming to this link. So to avoid this, what we are going to do is let's stop the simulation first and then we'll change the lane change distance of this particular connector to 30 meters. So then what happens is the vehicle will not be able to like see the emergency stop position before even coming to the connector. They will utilize this particular lane. So if we run the simulation, then we'll be able to see vehicles using this particular lane. It looks more realistic. Likewise, there are many things that you can change in order to tweak the driving behavior so that it looks more realistic. Okay, so let me go back to the presentation again. I'll explain why I did change the lane change distance. So what happens here is we have some irregular behavior happening at our model when the lane change distance is very high. This irregular behavior includes unrealistic slowdowns, and the merging lane will never be utilized. So all these things can be avoided by changing the default lane change distance of that particular connector. Okay. So usually by default, the emergency stop position is calculated by 30, like emergency stop position is calculated by the 30 percentage of the whole connector length. So then if you want to change all these parameters, then you have to double click on the connector and then change it here. Okay, so by changing all these values, you will be able to like change the behaviors of the vehicle and prevent irregular behaviors from happening. Okay, so if you have any questions, let's like keep it at the end. We'll be answering your questions, and let's move on to the next one. So when you're modeling highway, like after modeling your geometry and adding in your highway demand and then routing all the vehicles, you need to make sure you're using the right driving behavior models. So if you take Vissim as an example, like if you take Vissim like driving behavior models as an example, we have three different models. So we used to have only two, and since 2025 we have another one more behavior model. So this three behavior model includes Vietnam 74, Vietnam 99, and ACC, which is adaptive cruise control. So here Vietnam 74 and Vietnam 99 are the two models that can be used for a normal drivable vehicles. But ACC is for autonomous vehicles. Is solely prepared for autonomous vehicles. So the car following models Vietnam 74 and Vietnam 99 can be tweaked so that it matches the highway behavior of all the vehicles that we see in the highway. So if you take Vietnam 74, the car following behavior of the cars in Vietnam 7 that has Vietnam 74 behavior model assigned to it is calculated with the help of this particular formula. What you see here is the formula that is used to calculate the minimum headway. So this minimum headway can be calculated by this formula, which consists of standstill distance, additive part of safety distance, and multiplicative part of safety distance. And z is the normalizing value. It will be between 0 and 1, and V is the current speed of the vehicle. So based on each of the vehicle's current speed and whatever value that we add to these kind of variables, the particular vehicle's car following behavior will be determined. So let's move on to Vietnam 99. So after seeing both the Vietnam 74 and Vietnam 99, we'll see a comparison chart and we'll decide which one to use. Okay. So if you take Vietnam 99, the minimum headway, which is B, is calculated by CC0, CC1, and the velocity. So here CC0 is standstill distance, and CC1 is the headway time. So here headway time is a vehicle. Headway time is decided by the speed of the vehicle as well. So if you see both the chart where the headway and speed is is taken into consideration. So the headway speed relationship looks like more of a non-linear curve for Vietnam 74 and a linear curve for Vietnam 99. So let's do some comparison. So when we compare Vietnam 74 and Vietnam 99, the headway speed relationship looks more non-linear for Vietnam 74 since it is a psychological model. And Vietnam 99, it looks like more linear because it's a kinematic model. And then if you see the behavior mode for both the models, Vietnam 74 has strong mode switching. So strong mode switching is from one mode to another, like braking to free flow to slow down. All these modes, what happens is there is strong switching, like sudden switchings. But if you see Vietnam 99, it is more of a smoother transition and it is a continuous switching. Okay, it's by observing all these values, what we can decide is Vietnam 74 is mostly usable on urban roads and it is usable in low speed environments, and Vietnam 99 is mostly useful on highways and it is very much used in high speed environment. Okay, so when you are calibrating your model for a highway context, you can use VRMN 99 for a better result. And then for calibration, I have shown you a chart, like I have shown you a table for easier understanding. So if you go to your Vissim and let's say you go to your traffic, sorry, let's say you go to your base data and then you go to your driving behaviors, you can see there is driving behavior for freeway, which is freeway is highway. So if you double click on it, you can see it will use Vietnam 99 because highways you can use Vietnam 99 for better results. So if you want to increase your density, you can lower your CC1. If you want to increase your jam density, like the congestion density, then you can lower your CC0. And if you want to increase your headway variance, like the variability for your headway, then you can use CC2. So by all these calibration parameter, we can understand that if you lower your values, you can get more aggressive behavior. Okay, so which is like the vehicles are like mostly closely congested, like closely following, and you can see there is a higher density over there. And if you use a larger value for your double VLMN 99 parameters or VLMN 74 parameters, you'll have more conservative driving behavior. So the parameter that I am talking about is these parameters like CC1, CC0, CC2, everything. Okay. So the parameters that will be affecting your model when it comes to highway modeling will be CC0, CC1 and CC2 because these are the parameters that determines your minimum headway. Okay. So then we move on to the some more parameters that we will be using to calibrate our highway models. One of it is cooperative lane change, and then other one is safety distance reduction factor. So let's take an example that is shown here. When you have three different vehicles, so let's first consider the vehicle A and vehicle B. So here, if vehicle A notices vehicle B has to lane change, then what it does is it will lane change itself first. So, like when vehicle A observes that vehicle B needs to lane change, then what vehicle A does is it will change its lane first to give room for vehicle B to lane change. But this lane change happens only if the route that A has to go is following the particular lane change. If it is going to the lane one, then if it is still be able to reach its destination, then A will lane change. But A will not lane change if that particular lane is not under its route. Okay. If the lane change is useful for that particular vehicle, then vehicle A will lane change for vehicle B. If it is not useful, then you will see vehicle A might slow down or move faster so that it can give space for vehicle B to lane change. Okay, so if you see like for these kind of scenario, what happens is vehicle A will see vehicle B wants to lane change, then it will calculate the safety distance. If the safety distance is okay, and if it confirms that changing to this lane will be helpful for it to reach its destination, then it will lane change so that B can lane change after that. Okay, then we go to safety distance reduction factor. So this distance reduction factor is like for every vehicle, there will be a safety distance that it will be maintaining with other vehicles that are on the next lane as well as it is with the preceding vehicles. So when a vehicle is lane changing, what happens is this particular safety distance might reduce. Okay, so usually we will have a particular parameter called safety distance reduction factor where you can specify a value between 0 to 1. Okay, let's say you are specifying the value as 0.60. It means it can reduce its safety distance 60%, up to 60%, so that it can give way for the vehicle A to lane change. Okay, so if you see this particular C has a safety distance of this much, so let's assume it is like 6 meters, or like let's assume it is 6 to 7 meters. Then if A needs to lane change, if you specify the safety reduction factor to be 0.60, then what happens is it can reduce 60% of its safety distance factor to give way to vehicle A for it to lane change. So these are some of the factors that you need to consider when you're when you're modeling a highway, because lane change is one of the very important parameter that you need to control in your highway. Because if you just model your highway without changing or calibrating your driving behavior, then you will see irregular lane changes everywhere on your model, which causes congestion, and you will not be able to rectify it that easily. So if you want your model to be closer to reality, then you need to specify all these parameters perfectly so that it replicates whatever that is happening in the real time. Okay, so the calibration that you need to do when it comes to cooperative lane change and safety distance reduction factor will be, when you want lane changes to have a smaller gap, then you can decrease your safety distance factor. So if you keep it as 40%, then what happens is 40% of the safety distance will be kept and remaining 60% will be given so that the other vehicle will be able to lane change. And if you want to keep the lane change to have lane changes to have a larger gap, then you have to increase your safety distance, maybe keep it above 0.60, can be 0.80, 0.9, anything, but you always need to keep it under 1. Okay, so decrease lane change congestion in auxiliary lane and increase lane change congestion in the adjacent lane. When you want to decrease the lane change congestion in the auxiliary lane, and if you want to increase it on the adjacent lane, then you can activate cooperative lane change so that vehicle will see if it is cooperative to lane change, then it will lane change. Okay, if it is like safer to lane change, then it will lane change. If you want to increase the lane change congestion in the auxiliary lane and decrease it in the adjacent lane, then you can deactivate the cooperative lane change. So this one you can find it in the lane change tab. in your driving behavior, and you can make sure you check it or uncheck it based on whatever condition you want it to have. Okay, then we move on, like we are done with the driving behaviors, the major driving behaviors that needs to be adjusted for highway modeling, and then we'll move on to active traffic management. So here we are controlling the traffic in the highway with the help of features that are present inside Vissim. So the first thing that we'll be learning about is vehicle actuated programming. So the vehicle actuated programming in like in a normal traffic modeling context is a programmable signal that can be used to control various things inside your simulation. So based on your signal or based on the traffic flow in your network, you'll be able to control certain parameters in your signal. So whatever we'll be doing is we'll be playing with the signals. So for VisWap or WAP, vehicle actuator programming, to work in Vissim, we need a program file called wap216.dll. So this is the program file that will be available by default when you have a Vissim license. And whenever you want to run your Vissim model, you need two different files. When you want to run your Vissim model with VisWap, you need two different files. The first one will be logic file, and the second one will be signal and interchange definition file. So this file will have all the details that Vissim needs to know when it comes to the signal, like how many number of stages, what is the interstage, and how long will be the interstage, everything. So I hope everyone know about like VisWap already. If not, like you can learn it with the materials, or you can um, ask us for a training. We'll be able to train you on VisWap as well. So usually when VisWap is running, it will run for every second of the simulation. So every second, once the vehicle has moved from its original position of the previous second to a different position, then VisWap will be called to run. Okay, so VisWap will always run for every second. Okay, so VisWap can be like a program like VisWap is a vehicle actuated programming that can be created inside Vissim. So if you want to do a VisWap programming, you need to have the program called VisWap. Okay, so it should look something like this or something like this. Okay, it should look either of this color. So you can open this. So when you open Viswap, you will have a gray box like something like this, and if you create a new file, you will have a window that looks something like this. Okay, so here is where you can write your vehicle actuated programs. So it starts with all the objects that you can use, and then it will start with the program editor. Here is where you can write the program. So program as in what happens when particular condition is met, and what should be happening to my model. So all these you will write it here. It is more like writing a Python script or like some programming script, but you are writing in terms of a flow chart. And then the next one will be parameter window, and then the next one will be variable window. Here is where you can define your variables, and the next one will be expression window, and you will also have subroutine. If you don't see it, you can see it from here. Mm, Yeah, you can hear. Okay, so if you don't see a subroutine window, you can go to window and then click on subroutine. So you can see the subroutines as well. I hope everyone knows what is what, but just to give you a small idea, Like here is where you will write your programs, and parameters are the parameters or the variables that you will be using in your like in your program. And then arrays, if you have like too many values, then you can use arrays. And then expression, if you want to use any formulas, you can write it here, and then you can just use the variable name of the formula. And then subroutines are the functions, different types of smaller functions that you will have. So each of the subroutines are created as a separate file, and then you can call them from here. Okay. So these are some of the windows that you see in this web. So let's move on to the next one. We are going to learn some examples. So the first example is on hard shoulder and variable speed limit. So before going to the example, let me explain how hard shoulder works. So if you see, let's say for a highway, we have a hard shoulder for a shorter length. Okay. So this hard shoulder, like it will look something like this. So we have a link here, one link here, and then another link here, and then we'll split the link somewhere here. So you can just right click and then you can say split link here, and it will be split here and here, and you can extend this particular link to have 4 lanes because we need to have a hard shoulder. Then you can create a dummy connector over here. So this dummy connector will be acting as two different, like acting as like connector that helps to route the vehicles on first route. So the first route will have only these 3 lanes connected. You can do that with the help of this dummy connector. And then the second route will have 4 lanes connector, which you can do that by placing the intermediate point of the route to this particular link. So I'll show you how you can do that. First, let's see the example. So I'll open Vissim again, and I'll go back to the model file, and I can open the hard shoulders. Yep. So if you see, this is the model, but in this model, you will be able to see there are two different partial routes. Okay. The first partial route is a normal partial route that is created all the way till here. But if you zoom in, you can see this partial route only uses this particular connector. And let's see what is happening to the second partial route. So if you see, this partial route uses all these whole link. Okay. So it means we have a hard shoulder here. This hard shoulder will be activated only during some conditions, only when some conditions are met. So let's analyze what are the other things that is available. We can see there is signal controller, and if we double click the signal controller, we can see the signal controller is configured as WAP, plus you can see there is a logic file added, plus there is interstage file, which is logic file. As I told you, it's a WAP file, and then there is interchange file, which is .pua file. Okay. And this particular program file will be available by default, so you don't need to adjust anything on this file. Okay. So let's close this. Okay. So what we are doing here is we are going to use web programming. For any web programming to run, you always need a signal head. So we have created a dummy link, and we have placed a dummy signal controller. This you don't have a, like you don't have a choice, because whenever you want to use that programming, irrespective of whether your model needs a signal controller or not, you need to place it. So this particular example can be done with the help of attribute modification or COM interface as well. Just for you to understand, we have WAP, we have implemented using WAP, I'll show you how you can do it in attribute modification later. Okay, so just understand that we have two different route. So for these two different routes to be created, as I told you in this example, we'll have a dummy connector first. So to have a dummy connector, what I'm going to do is, there is already a connector and I'm creating a another connector on top of that particular connector. So this connector will be acting as my dummy connector. So when I'm creating my partial route, you can use static route as well. So it is up to you to decide based on the condition that you are using. So if you see this partial route, what I did was, let me go to my vehicle routes and then select partial route. Okay. So if you see this particular partial route, where partial route 1, you can see the shoulder and the another connector is not selected. But if you see this particular partial route, only this connector is used. This can be done with the help of using this intermediate point. So you can just press Control and right click, and then you can hover so that you can so that you are selecting the right connector. Okay. By default, if you create a partial route, it will use the smaller connector, and if you want to use the larger connector, you can just hover over to the last lane so that this will be used. So we have two different routes. Okay, now we have to write a condition to make sure when a particular route needs to be activated. Because if you see the presentation, you can see there are two different like conditions. One is shoulder open, and then the other one is shoulder closed. Okay, for these things to be for these things to be satisfied, or for these things to be calculated, what we need to do is we need to write a viswap file. So let me go back, go to hard shoulders, and you can see there is a program file that is already here. I'm opening with viswap, and here you can see a complete program that is written in viswap. So I hope everyone knows the basics of Viswap. I'll just explain what is happening here. So we just initialize it, and then we are going to check if we are going to set the route. So by default, the vehicle has to use the only the 3-lane connector, and only if the demand is very high, then we'll be changing the 3-lane connector to use the 4-lane connector. So to do that, first let's define what is default. So that by default thing is 1 1 1, like set the route 1 1 1, which means, go back to this, set the route 1, which is number 1, and vehicle route decision number 1 to have a relative flow of 1. So for this function, like for the functions, like for understanding the functions, you can go to any of these location, and then you can like any of these location where you have a statement or a condition or anything, any of the flowchart place, then you can just double click, and then you can say wrap function. So here you can just go directly to all, and then go search for set route. If you search for set route, it will show you the small description of what this particular function will do. Sets the relative flow of the route number of the routing decision number in the current travel time to a relative flow. So the first one is route number, decision number, relative flow. Okay. The second one, what we are seeing is set route number 1, decision number 2 to have a relative flow of 0. So that is what has been done. And then here for this example, we are going to also do the variable speed limit. So if the flow is very high, then we want to control the speed limit. So, but here if you see, by default, we are setting the desired speed to be 130. The desired speed that you are seeing is for desired speed 1, and for the vehicle type 10, which is cars, set my desired speed to be 130, and for the desired speed 2, for the cars, set the desired speed to be 130 as well. So likewise you are doing for all this. If you want to see what it means, then you can just go to web function, just right click and open web function, and then you can search for set desired speed. The first is distribution number to the vehicle class to the desired speed decision. Okay, so you are setting for different desired speed, and then you are saying the signals to be red. So it's just for your visual purpose. So we are setting the signal to have red. By default, this particular signal will be red. Okay, only if the q reaches the maximum value, then the signal will be set to green. So let's move on to the next condition. So I'm asking this program to do the calculation every minute. So what I'm doing is counting every minute, and if it is not every minute, then I'm like increasing the count, so that by the end of every minute, which is by the end of every 60 seconds. So first 60 seconds, it will be like it will have S, and then it will go calculate the next one, which is queue vehicle, the number of vehicles inside the queue. So what we are doing is front ends. Front ends will give me the number of vehicles that has crossed that particular location. This location, what you are specifying is a detector's number. So detector number 1, detector number 2, detector number 3. Sorry, detector number 1, 2, 3. Okay. Whatever you are specifying here is the detector's number. So I am calculating the number of vehicles that has crossed that particular detector for that 1 minute, and then I am multiplying it by 60 so that I can convert it into a hour. So hourly rate. So I'm calculating for 1 minute and then converting it into hour, and then I am storing all these value into Q vehicle. And after I calculate the Q vehicle, then I am going back here. If my Q vehicle is greater than Q on is my maximum Q that I can see. So here you can see the Qs that I can have. So Q1 should be 5,500 vehicles per hour. Q off is 4,700 vehicles per hour, and there is different values that you can use. For now, just note that we are using program number 1. So 5,500 will be my maximum queue that I can see, and maximum flow that I can have, and queue off is the minimum flow that I can have. So if it is more than the maximum flow, then what I'm going to do is I'm activating the shoulder, which is I'm going to use the 4 lane as well. So I'm changing the relative flow, and then I'm reducing the desired speed of the vehicles so that they are slowing down, so there is lesser congestion. And for visual purpose, I'm changing it to green. Okay. And if it becomes, once the queue becomes lesser than my maximum queue, then I'm slowly increasing the speed. And if the queue is already less than my minimum queue, but still the current state is green, then I'm going to switch it back to amber, so that later it will switch back to red. Okay, it's just for visual purpose. So this is how you do vehicle actuated programming for a hard shoulder and variable speed limit example. Okay, I hope I'm clear. If you have any questions, you can ask me later after the end of this webinar. Then we move on to the next example, which is ramp metering. So ramp metering is like one of the most important things that you need to know when you are doing highway modeling, because the main purpose of ramp metering is to control the number of vehicles that are entering from a random road, like random, it can be a normal urban road or it can be a city road that is connecting to the highway. So whenever a smaller road is connecting to the highway, you need to regulate the flow of vehicle into the highway, because you should make sure it is not congesting, like it is not making the highway traffic slower. So you should always maintain the flow of highway traffic, and you should always also let in your traffic from your minor road. So to regulate these kind of traffic flow, you need ramp metering. So also, you can use this ramp metering to decrease the demand in the freeway. If you notice that the traffic from the minor flow is affecting the demand of this particular highway, then you can regulate it or you can decrease it by making by stopping all the vehicles here. And you can reduce the platoon size from the upstream traffic signal. So you can reduce the platoon size, like the number of vehicles that are going together, so that it is easier for you to control them later in the traffic. Okay? And it is also used for safety, because let's say like the flow of the highway vehicle is always bit faster than a flow of vehicles from the minor road. So to control these two vehicles from colliding with each other, we can use ramp metering to stop them before like the vehicle passes. Okay, here like always, we in ramp metering we use 1 second for green and 1 second, like minimum cycle length to have is 1 second for green and 1 second for red and 1 second for yellow. Okay, the meter capacity for a ramp metering highway is 900 vehicle per hour. And if you open Vissim, and if you open your, like, let's say I'm opening my next example, so I'll go to my ramp metering example and I'll open it. So for this particular ramp metering, I already created everything from scratch. But for your case, you can use your function, like easier function that is already in Vissim, which is called as create ramp meter. So if you use this function, you can create a easier ramp metering facility without creating everything one by one. Okay, if you see, there are like a lot of parameters, so let's learn what each parameters are meant for. Okay, the ramp metering that is used in Vissim follows a strategy called alinea strategy. So this alinea strategy, I'll explain it later after we move from, like, after we learn what are these variable say what variable means. So the first one is met evaluation interval. So met evaluation interval is then evaluation intervals, like how often you want the model to check. Okay, so if you, like, by default we'll always keep the model to check the traffic flow every 60 seconds, which is 1 minute. Okay, rate q disperse, so meter rate q dispersion, met rate q dispersion is meter rate q dispersion. It is the maximum target flow you are trying to achieve in highway per lane basis. So per lane, how many vehicles you are trying to achieve. And then desired occupancy, desired occupancy is the desired occupancy that you want to have in your highway, which is 25%. It's the default. You can adjust it up to 100%. And occupancy of Q. So how much Q occupancy you need to have, which is 50%, which is the default. And then, like, you're specifying all this so that you can control your queue. So like desired occupancy should be 25, and then the activation occupancy, like when the ramp metering needs to be activated, is when it is 50%. and when it needs to be deactivated is when it is less than 10%. Okay, by default it can have 25 percentage of flow, and if it is more than 50%, then you have to activate the ramp metering. If it is less than 10%, then you can deactivate the ramp metering. And regulatory parameter. So regulatory parameter is the smoothening factor that you'll use in your ramp metering facility. So 70 to 120 is the default value. So 70 is the default when you create your new ramp metering facility. And then generate Q detector. So this generate Q detector is like when you want to have these Q detectors in your model. So in order to detect the number of Qs, so if you select this, then you'll have Q detectors. And then Q detectors at the position before the stop. So whether you want to have these Q detectors or not. So you can just like decide whether you need to have it or not, and how much the desired this distance should be. So by default it is 100. You can go up to 200 or 250 to have a realistic value. Okay, so let's learn about Alinea strategy first before we move on to seeing how ramp metering works. Okay, so Alinea strategy is one of the strategy that is used for all ramp metering control. So this is a feedback type of algorithm. So as you know, BISWAP is used for mostly feedbacking algorithms, like whatever algorithm that requires feedbacks. Viswap is the best way to program it. So Alinea is one of the feedback type algorithm as well. So when you take a ramp metering, like in older way, what they usually do is they'll have a signal head at the minor road, and what they'll do is they will have this particular signal to have fixed time. So for every 30 seconds they will let the vehicle flow, and after 30 seconds is over they will close this particular signal, close this particular traffic from going into the highway for like certain amount of time. Let's say it's 20 seconds, but it is not efficient. So that's why we are using vehicle actuated programming with Alinea strategy here. So Alinea strategy has this is the formula that Alinea strategy uses. So here RK is the current cycle ramp metering rate. So ramp metering rate is being used here. So R of K is current cycle ramp metering rate, and RK minus 1 is the previous cycle ramp metering rate. And then Kr is the constant or the smoothening factor that we will be using. It's the regulatory parameter. And O is the desired occupancy downstream at the highway. And then O out is the measured occupancy. Okay. What happens is this will try to maintain the desired occupancy at the highway. Okay. So the one that you see on the right side is the WAP programming that was created. So let me go open the WAP program first, and then I'll explain how the WAP program works. Yeah. So if you see, this is the WAP programming. Whatever you see on the left side is the flow chart. So let's start with how it works, and then I'll show you how it looks like. Okay. So first one is like we are beginning the ramp metering. So it's the function. So you can begin it, and then we are initializing everything with off. So the signal that is placed here should start with off. Off as in it is in red. Okay, and then we are calculating the cycle second. So because we need to play around with the signals a lot, so we are calculating the signal second. So the signal second will start with 0, and then the cycle second will start with 0, and for every cycle, like once the cycle second is over, it will reassign itself with 0 again. Okay, so we have cycle length. Cycle length, it should be it should be specified by you, like based on whatever cycle length that is followed in your country. So for this particular example, I think we should have a cycle length. Let's go to signal controller, and then you can see in the detector record, you should have cycle length. If you don't see it here, you can always see it here. So it's 60 seconds. So the cycle length is 60 seconds. And then for every 60 seconds, it will reinitialize itself with 0. Okay. And then we are storing the cycle second. I'll tell you why we stored the cycle second later. And now we are calculating the occupancy at the detector number 2 and 1, because we are using array. So we have two different arrays, and then we are going to calculate what happens when there is detector value of 1 and what is the value for 2. So if you go here, you can see this detector has a port number. Like port number is the most important one, 2, and this detector has a port number of 12, and this detector has a port number of 11. So port number 11 and 12 are the detectors at the highway. So we are calculating the ramp metering rate by using the detectors 11 and 12. Okay, so we are calculating the occupancy at the highway. Okay, so this is just to plus the array, and then we store both the occupancy here. And we go here to calculate every minute. So here what we are doing is QRAM front end 9. Let's see where is 9. Where is detector 9? So detector 9 is somewhere here. So we have detector here as well, but this detector is used to count the number of vehicles that has crossed the signal head. So it can be bigger as well, but just for us to detect the number of vehicles, we have placed it very smaller. So if you see, the detector length is 0.0000 meter. So that's why it is very small. So we are using this particular detector rate to know how many number of vehicles has crossed this particular signal, okay, from the minor road. And then we are calculating the value that is the occupancy here, and then we are multiplying what are we doing, sorry, we are we are calculating the occupancy of here, and then we are storing it for the evaluation interval. Later, we'll be using this occupancy to test if it is matching the desired occupancy. So here, what we are doing is we have converted the occupancy into 1 hour, and then we are going here to calculate the current ramp metering rate, and we are going to compare it with the previous ramp metering rate and the desired occupancy plus the occupancy that is observed. Okay, so this formula is what you see here. So current ramp metering rate, which is CQ ramp, and then previous ramp metering rate, which is Q ramp, and then smoothing factor is KR, which is specified as KR as well. So you can see this value is mentioned as 70, and then occupancy, desired occupancy is said to be 0.29, and the O out, which is observed occupancy, is said to be what we got from here. Okay. Now we got CQ ramp. So we are now going to convert the CQ ramp to per hour basis. So dt is the time interval that we need to have. So we are doing for 1 hour basis. So 60 into dt, which is 1 hour divided by CQ ramp. So it will be like whatever value that you have into 60, which becomes like 1 hour basis. And then we are recording the value. I'll show you why we recorded the value, and then we reset the observed occupancy to be 0. Now we go back here. Once we see the cycle length is less than 4 seconds, so now we have to configure the signal control logic. So here, if the cycle length is calculated greater than 4 seconds, if there is a demand in the ramp, then check for the current rate time. So we want to see here, like if you see, we want the vehicle to wait a maximum of 4 seconds, and then we want them to get green, because if there is a occupancy here and if there is 4 seconds happening, then we after 4 seconds we want to give this particular thing green if there is a higher demand. Okay, if there is a higher demand here and if there is a lower demand that is observed at these two connectors. So if the cycle second is 4 and if the demand is okay, then we switch to red amber and then it will switch to green. And if it is already in red amber, then we need to switch it to off, which is make it red. If it is already in red, then we need to make sure if it is less than 4, if it is less than 4 and it doesn't have demand, then we can switch to amber and it will after switch to red. If it still continues to have demand, then it will still continue to have green. Okay, so this is what we are doing for the signal control. So whatever we did on top was to calculate the demand, and after calculating the demand we are playing around with the signals. Okay, after this we record the cycle length and we also record the ramp hour. So we recorded all this because we wanted to see everything. So let's just go to evaluation window, SC detector record. Click OK. Let me bring this to the right side. So whatever values that I have recorded. So if you see, I have recorded O out as in occupancy at the highway, and then I have recorded the cycle length and I have recorded the Q ramp per hour. So whatever you are seeing here is the outer lane occupancy, the highway occupancy, and then the cycle length, and then the Q ramp. So let's run it for some time. And Q ramp that is observed is only like it's way less. So we just run it for some time. So if you see, if the demand is higher, then it will stop. If the demand is lower, then automatically you will see this particular thing turns green. And for every 60 seconds, you will see a value. So for next 60 seconds, there will be no value. That the value is the occupancy at the highway. So after 60 seconds, you will see another value coming in. So it's per minute time interval, sorry, per minute occupancy rate. So 37 per minute. It will continue to run. And if the demand is high, then you will see this particular vehicles getting red and then they'll stop till the demand is getting slower, like lower. Okay. So this is how we do ramp metering. Then we move on to the next example, which is variable message sign. So the next example is variable message sign. So let me open the example first. So what we are going to do is we are going to collect the data, and based on the data that has been collected, we are going to use user defined attribute and attribute modification to display variable messages on this signboard, and we are also going to control the speed and the flow of the vehicle at these lanes. Okay. So let's go here. If you open the model, you can see there is some desired speed distribution that is already created. So if it is blank, like if all these things are blank, then it means 80 kilometer per hour. If there is like whatever you see here is means no limits. So if it is no limits, then it means 80 kilometer per hour as well. Okay, but if you go to user defined attribute, here what we are doing is we have we are checking the queue, we are checking the flow. Q means flow at 60 kilometer per hour, and Q off like flow like off the flow if it is like if it is running at 60 kilometer per hour, and for different speed we are checking it, and we are going to check few other things. The first one is variable message signs number, variable message signs speed, and variable message signs traffic flow. And we also have variable message sign speed but in desired speed decision object, and we also have 3D traffic signals. So why we are using 3D traffic signals is because Vissim doesn't have a variable message sign object. Instead what it has is 3D traffic sign. So if you see, for in 3D traffic sign, this whole thing is considered as a traffic sign. So let me open this and let me make this a bit bigger. Okay, I'm not sure why I'm unable to open like make this bigger. But if you see this particular 3D model of a variable message sign, you can see everything is modeled separately. So you can see there is one arm which is in H shape, and there is so many traffic signs. So each of these box that you see is a traffic sign. Okay, we do this because we want to control these traffic signs, like each of these boxes as a traffic sign later using attribute modification. So let me cancel this so you can understand these like this whole structure is a 3D traffic sign, and we have defined all the user defined attributes, and then we go to attribute modification. So the first thing that we are going to do is we are going to calculate the traffic flow, and we are going to calculate as PCUs. Okay. So what we are going to do is we are going to do evaluation configuration, and we are going to collect the data collection. And as I always told you, most of the data that we collect or most of the evaluation that we do it every 60 seconds. So I'm just going to say 60 in the interval, and I'm going to open the attribute modification. So here to calculate the PCU, I need to go and refer to a different object which is data collection measurement object. So to refer to a table of a different object inside an object, you need to use table lookup function. So to like use the table lookup function and then refer to the data collection measurement table, and then store the table inside a variable DC. And in the DC variable, you can see there is an attribute called VMS number. So you need to store DC's like a value from a DC to a variable called VMS number. So the number is NO. Okay. So what we are doing is we are going to like see what is the value on a particular number and then storing it inside the variable that we have. And we also refer to different values inside the data collection measurement, which is number of vehicles. VEHS is number of vehicles that are from current run but last time interval, and the number of vehicle, like the vehicle type should be 10. 10 as in 10 refers to car. And then we are doing the data collection measurement as well for current current run last interval, but for 20 vehicle type. 20 vehicle type here is truck. Okay. To convert like things like to convert a truck into PCU, we need to multiply it by 2, because like that is how we always calculate PCUs per minute. And then we have to multiply it by 60 because it runs every 60 seconds. So every second, so we need to calculate for per minute basis, so we multiply it by 60. We use this particular variable, so the variable, like the result that we get from here, we compare it with the user defined attributes later. So then we move to the next one, compute new speed. Okay. When you have a flow higher than any of these values, then you need to specify a different speed for that value. 141 means blank, because all the vehicles are higher than 140 kilometer per hour. The vehicle speed will go higher than 140 only if the traffic flow is lower than our desired occupancy, desired flow. Okay. So if the traffic flow is very low, very high, then we lower the desired speed to 60. And if it is like for different values of traffic flow, we are assigning different desired speed. So if you see something that is more than 140 means the desired flow is really low. Okay. Something like this. We also do speed assignment for both cars and trucks. So we already like have VMS speed value assigned already, so we use the same thing, and then we assign it for cars and HGVs. Then we move on to 3D traffic sign. So here is where for different values we are assigning different 3D signs. So to see all these 3D traffic signs, where you can go is you can go to texture file. So go to your 3D traffic signs and go to texture file names, and here signal head pictograms, sorry, not signal head pictograms, it's signals. In the signals, if you scroll down, you can see all the different types of signs for different speeds. Okay. So whatever we are changing here is for different types. So like show VMS sign type 1. So type 1 is this one, and type 2 is this one. And here for 140, something greater than 140, you can keep it as blank. But if it is 140, then you need to assign it with end of all previously signed. And for 120, you need to specify 120 speed limit 3D sign, and for 100 it is 100. So likewise, you have to specify for different speed limit what particular 3D sign must be changed. Okay. So let's see what is the next one. Next one is also same, just that we are doing it for VMS type 2. Type 2 is here. Okay. So now if you go here, you can verify all the names of the 3D, like all the names of message signs. So you can see for 90, it is 90 speed limit, 100 speed limit. Likewise, they have specified it in attribute modification. So attribute modification is very similar to whatever you see in Viswap, okay? But you are doing it inside the model itself. So let's go to presentation, result list, sorry, evaluation, result list, data collection measurement. And then we can take down all these and just go to vehicles. No, data collection measurement, vehicles, current run, these two. Make here. Yes. So based on this, the traffic flow will be controlled. So if you see now the current traffic flow is much lesser. So we are running it in a desired speed of 120. And if the traffic flow increases, then automatically you will see based on the traffic flow, the variable message sign changes with the help of attribute modification. Okay, yeah, so that's it. That's all for the training session. So let me know if you have any questions.
Yeah, so I'm looking at the Q&A box. There are no questions so far, but in the meantime, yeah, I think Sharan went through a lot of things during his webinar, a lot of content. So we would really appreciate if you could fill in our post-webinar survey. I'm flashing it on the screen right now. Sorry, yeah. So if you could just take 1 minute of your time to fill in this survey, the link is also in the chat box. But if you have any questions, do put it in the